Live on YouTube.
We are live on TikTok.
Live on TikTok.
All right, have a great show.
Thank you. Almost said you too.
But I will. I'll be around. I'll be on.
All right. Hello, hello, hello. All right, guys, let's jump right into it. Start off focusing on trig tonight. And a lot of people are getting to that point in their curriculum, so including myself. So let's go ahead. This is a special right triangle problem. So go ahead and try to figure this out. Ooh, let's do it in radians. Start with degrees first. Hopefully you can all read that. It says 30 is up at the top and then 60 is down at the bottom. I'll go over it in black. There we go. And try them. Oh. All right, so this is a special right triangle. And it's special because it's a 30, 60, 90 triangle. There's two types of special right triangles. We've got 30, 60, 90, and we've got 45, 45, 90. So in a 30, 60, 90 triangle, what's special about it, what's kind of interesting about these is that they always occur in the same ratio to each other, the same relationship, right? So they've got to fit into like x squared plus y squared has to equal 10 squared, right? Now, that's easy to follow. Like the Pythagorean theorem is easy to follow when you have two sides, right? You can figure out that third side. But here, what we've got is we've got 30 degrees and 60 degrees and 10. So if I weren't given these angle measurements, I may not be able to, I wouldn't be able to figure out these other two sides. But since I'm given these angle measurements, I know that it is a special right triangle. And special right triangles always exist in the same kind of arrangement. Okay, so this one up here would be 30, this one's 60. So if we draw this right in the same kind of the arrangement as the other one right there, right? So Kim, you're saying that makes the side labeled Y look shorter than the side labeled X. So it actually is. It's Y is going to be shorter than X. And the reason is because this angle up here is 30 degrees and this angle here is 60 degrees. And so 30 degrees is going to be across from a shorter side than the 60 degree side. Now the longest side is going to be the hypotenuse, right, which is 10. So they're both going to be less than 10. But across from the 30 degree angle is going to be the short side or the short leg. And then the 60 degrees is going to be across from the long side or the large side. So across from the 30 degrees, if we say this is like the value of A, okay, then up here the hypotenuse is always going to be 2 times A. And then this long leg is always going to be whatever A is times root 3. So over here, we've got 10. So 2A is 10. Which means that A is going to be 5. Right? So Y equals 5. And then X, we have our A value is 5. Then X is going to be 5 root 3. So with special right triangles, once you know that relationship in there, it gets really, it gets really simple to kind of figure out what these side lengths are. Let's see. This year I taught special right triangles as similar triangles as opposed to multiplying the short leg by radical 3. Okay, so math teacher, tell me more about that. So just thinking about that, it's like 1, 2, and root 3, and then you just multiply by whatever the scale factor is. Is that what you mean? So I can see how that would be really helpful, would be to kind of teach it that way. Okay. So these special right triangles are usually kind of like the precursor to when you're starting about trig, getting into trigonometry. So let's look at a problem here. Okay, so if I've got just kind of looking through. Well, yeah, let's stick with the special right triangles. I don't know why these triangles are coming out so bloopy. So if you guys are just joining us, go ahead, and if you have any questions or any comments or anything like that, anything that you want to take a look at or you want me to go over, let me know in the comments and we can get into it. So I usually just sort of start out with kind of what I'm doing in my classes that I'm teaching, just to kind of get the ball rolling. But if you have something specific that you want to get into, put it in the chat and we can take a look at it. Okay, so we're going to say that these are both congruent, which means it's an isosceles triangle, which means that these are both 45-degree angles. Okay, and then we're going to say that this side length is 4 root 3. I'm going to call this one X and this one Y. Okay, so go ahead and figure out what X, I'll give you guys a couple minutes to figure out what X and Y are. Scarlett, what do you need? Give me a little bit more information with algebra 2 polygons and quadrilaterals. Okay. Oh my gosh, I almost wrote on my paper. I don't want to do that. Okay, so I see ambiguous case. And we'll probably talk about like law of sines and law of cosines. Can definitely do that. Let me see. So Henrik, SOHCAHTOA. So you could do SOHCAHTOA, but since it's a special right triangle, and even on the one that we did before, you could use SOHCAHTOA, which is the right triangle trig ratios. But if you recognize that it's a special right triangle, it makes it a little more efficient when you're working through these things. Finding the missing measures with given ones. Okay, well, Abs, I'm not going to be able to teach you all of AP Stats right now. Is Y 12 or 8? Okay, let's see. It is a 45, 45, 90. All right, so with a 45, 45, 90, so again, it's a special right triangle. So when these angles are both congruent, which means they're both 45 degrees, right? These sides are both going to be equal to each other. And then this side out here is going to be a root 2. So it's a times root 2. So in this case here, what we've got is our a value is 4 root 3. So that means that x is going to also equal 4 root 3. And then y is going to be 4 root 3. I'm going to write it over here. Y is going to be 4 root 3 times root 2, which gives me 4 root 6. Okay. There we go. Ooh, cereal, you've got the blizzard coming your way, huh? We got a little bit of snow today in Michigan, but nothing like what New York is gonna get. Woo! Okay. The one only original, the 2y, the 2 for the hypotenuse, that's for a 30, 60, 90 is where the hypotenuse is twice a, is 2a. Okay. All right. Yeah, Sean, these are special right triangles. Yep. Oh man, Liam, you guys already got a foot of snow? Whew. I know that's supposed to be what they're getting in New York City. Do YK slope intercept? What do you mean YK slope intercept? Is there a simpler way to simplify square root? So Rhea, there's not really a simpler way to simplify square roots unless you get a NumWorks calculator that'll do it for you. But what you can also do is if you have a TI-84, you can use your y equals function to do like the number divided by x squared, and then that will do that. But there's not really a simple way to simplify radicals. Okay, so on this side, so x is 4 root 3, y is 4 root 6. That's what these three side lengths are. Okay, all right, so I'm seeing a lot of trig questions, so let's go ahead and let's get into it. So special right triangles, again, are sort of like the first step into trig. Trigonometry, hold on, need to, there we go. So trigonometry is joining together the angles and side lengths of triangles, and usually you start with right triangle trig, okay? So right triangle trig is where you have a right triangle. And the one thing that we all know about right triangles is where you've got a squared plus b squared equals c squared, right? So the Pythagorean theorem is going to be what's true, right? So a right triangle has to have a specific relationship between the side lengths. Now, what you don't always learn first is that that specific relationship between all the side lengths is reliable or is reliant on specific angle measures as well. And so if you know the angle measurement and you know one of the sides, you can figure out the other things, the other sides, because they have to fit together with Pythagorean theorem. Now, what this is these are the trig ratios. Okay, so trigonometry relies on these ratios. Sorry. So the thing that we first use is we use this 0 with a line through it. We call that theta. Okay, so that's a Greek letter theta, and that kind of stands for the angle that we're looking at. Okay, so the angle in question, the angle that we're focusing on. So if that angle is theta, this side length is always going to be the hypotenuse. Okay, so we've got the hypotenuse and it's always across from the 90-degree angle. Okay, this side, the other two legs have names for them that are relative to the theta. Okay, so it depends on where they're related, where they are in relation to the theta, what we call them. So this leg, or the leg that helps form the theta angle, we call that the adjacent. Okay, and then the leg that's across from it, we call that the opposite. So the trig ratios, I'm only going to focus on the three main ones, because those are the only three that you really work with that frequently, especially like in the high school math realm where we're kind of hanging out. Okay, so the trig ratio. So the easy way to remember this is SOHCAHTOA. So SOHCAHTOA, the way that you can remember these. So sine of theta. So the sine ratio is the opposite over the hypotenuse. Okay, so sine is opposite over hypotenuse. Now the sine of whatever angle that is always going to be the same ratio. Okay, no matter how big or how small the triangle is, the ratio is going to be the same, right? So sine theta is opposite over hypotenuse. Cosine theta, you look up here, it's the adjacent over the hypotenuse. And then tangent theta is the opposite over the adjacent. So those ratios are always going to be the same. Whoops, it's kind of sliding over, sorry. Okay. So for a right triangle, they're not always equal, no. They would only be equal if it was a 45, 45, 90 triangle, okay? So with these, if you're given the ratio, you can figure out the other sides. If you're given one of the side lengths and an angle, you can figure out the side length, okay? So let's take a look at that. So if we've got a triangle, let's see. Okay. So Rizzy, we're doing trig. Woo woo! Trig on a Sunday night. It's perfect. Okay. So I'm going to have this triangle. This might not work. Okay. Now, I don't ever draw these to scale, right? We're not drawing them to scale. But I'm going to say this is my theta. Well, yeah, let's start with that. And if this is 7 and this is 5, right? So first of all, how can we find that third? How can we find that third side? All right, we need to figure out what our hypotenuse is. Okay. So I would do 7 squared plus 5 squared equals h squared. So that's 49. So that's 7 squared plus 5 squared. What's happening? 7 squared plus 5 squared, which is 74. So 74 equals h squared. So that means that it's the square root of 74, which equals h. And I don't believe that, no, that cannot be simplified down. So my h value is root 74. So if I needed to find all the trig ratios for this side, or for this triangle, now I have enough information to actually do that. Okay. So sine theta is going to be my opposite over my hypotenuse, which is 5 over root 74. Now there is a problem with this, right? So you technically can't have this root 74 underneath. Can you guys read this blue? I can't tell from my screen if the blue is okay or not. Let me know in the comments if I need to switch it. So I've got sine theta equals 5 over root 74. Okay, great. Okay, so I can't have a radical in the bottom. So what I have to do is I have to do something called rationalizing the denominator. Okay, so what I'm going to do is I can multiply anything I want by 1. So I'm going to multiply it by a version of 1 that actually gets rid of that radical in the bottom. Okay, there is absolutely, yes, who are you? Burnt toast. There is no good reason to have to rationalize the denominators. I am with you 1000%. So the reason that we are still rationalizing the denominators is because, well, we started out having to rationalize the denominators because at the time, a long time ago, calculators, when you were using like slide rule and things like that, you weren't able to do this if there was a radical in the denominator. But now with these fancy calculators, you can. But, oh, I am with you guys. So I don't really particularly care if my students rationalize the denominator or not, except I explain to them where it comes from and why we do it. And I want them to be ready because they still rationalizing the denominator on the SAT, on the ACT. And so if you don't see this and you don't understand rationalizing the denominator, you're going to get it wrong, right? Because you don't understand what that's doing. But still on the SAT and ACT, they still make you rationalize the denominator. I am with all of you. Like, it is silly for us to have to keep doing this, but you know, it is what it is. Okay. Yeah. Many professors, so Jacques, it's a good habit to do because when you get like, even on all the answer keys on worksheets and things like that, they still rationalize the denominator. So again, I tell my students, like, this is what it's coming from. It's the same thing. Like, if you're not sure, plug it into the calculator. You should get the same crazy decimal if it's the same thing. That's kind of how I look at it. But so what we're going to do is we're just going to kind of go over that. So to get rid of a root, I can multiply by the same root. So I've got root 74 over root 74. So root 74 times root 74 gives me 74 on the bottom, and then 5 root 74 on the top. Okay, so again, this is the answer that will be on the SAT or the answer key or something like that. Right, so this is also the same thing. Okay, so again, this is why I tell my students, like, where this is coming from, what we're doing, right, is that if you get this, but this is the only answer choice, you may not choose this if you don't know where it's coming from or what it is, right? Okay. All right, so now, what if we wanted to figure out what that theta is? Okay. Oh, actually, let me catch up on some. Let's see. Oh, thank you. You're awesome. Awesome. Okay, what math do you teach? I teach primarily geometry and algebra 2. We do an integrated math approach at my school, so I teach mainly sophomores and juniors. Intelligent, I do SAT prep. Yep. Yeah, so J4. Yes, so here's what we're gonna do. So if I want to figure out what theta is, okay, because again, remember, these are gonna occur in this ratio because this is the Pythagorean theorem, right? But also, we can use that to figure out what the angle is, okay? So what I can do is, I know that I don't want to deal with a radical, so I'm just going to use 5 and 7. So looking at what ratio I can use that has 5 and 7, I'm going to use tangent, okay? So I'm going to say that tangent of theta, I know that tangent theta is 5 over 7, because that's my opposite over my adjacent. Okay, now I can't just divide by tangent because it's like an operator. Okay, so theta equals, we use this thing, we do tan to the -1 power of 5 over 7. So it's kind of like the same thing as dividing by tangent, or arctan, right? It's the same idea. Okay, so then that's something that we just put into our calculator. So it's usually like the second tangent. 5 divided by 7, enter. So we get that theta is, we get 35.5376, on and on and on and on. So I would call this as theta is approximately 36 degrees. So a pretty good rule of thumb that I would say most teachers that are teaching trig usually do is side lengths are to the tenths, angles are to the nearest whole angle. Okay, now if I were to plug this back in 36, like tangent of 36 is not going to be exactly 5 over 7, right? Because we just rounded it, but that's okay. It's close enough, right? Is that the same theta representing the angle of a triangle inside a circle? Yes, it is. So theta is theta. Theta is what we use to talk about our angle of interest. Okay, so that's our angle of interest is theta. So usually you use x for your variable, right? Or like x and y for your coordinates. But theta is sort of like that given sort of marker, I guess, for variable or for angle. Okay, so somebody asked earlier about the ambiguous case. We can't really talk about the ambiguous case without talking about the law of sines. And the law of sines, I love doing this because the law of sines is how you go about solving a triangle that needs to, or that doesn't, that is not a right triangle. Okay, so I'm gonna get one of these. Okay, so the law of sines is based on the relationship between sine of an angle and its opposite side. Okay, so when you're naming a triangle, you use capital letters for the angles, and then for the side lengths, you use a lowercase version of the angle that's across from it. So the opposite angle there. So this is lowercase b, and this is a little c. Okay, so it gets a little bit easier when you're working these out. Oh, you got it. Good. You've got a test tomorrow. Excellent. Okay. So we're going to name, so angles are uppercase, side lengths are lowercase. Okay. So the law of sines is relating your angles and your side lengths. Okay. Because the relationship or the ratio between sine of an angle and its opposite side length is actually going to be the same for every single angle and side in a triangle. So sine C over C. And this flips too, right? You could do A over sine A, B over sine B, C over sine C. It works, right? It's just a ratio. Okay. So what you've got is you've got this ratio that you can use to solve all types of triangles. As long as you have an angle and a side kind of pair, okay? Avian, yeah, online one-on-one tutoring. Click the link in my profile and we can book a one-on-one tutoring for sure. Okay, so let's take a look at this problem. This is one that I did with my students last week, I believe, or no, yeah, last week. All right, so this is 52 degrees. This is 34 degrees. Remember, this is not a right triangle. Okay, so that's 52 and 34. This is X, and this is 10. Okay, so this angle, the information that we're given for this triangle is angle, angle, side. So we can use the law of sines, and we'll talk about the ambiguous case in just a minute. Okay. So if we take a look at this, right, we do have a complete angle side pair, 34 and 10. So I know that sine 34 over 10 is the same ratio as sine 52 over x. So if I set up my proportion like that, now I can get somewhere, right? I can solve that proportion to figure out my value for x. So I solve a proportion by doing cross multiply. So I have x sine 34 equals 10 sine 52. This is used for triangles that are not right triangles. Yep, this is what you use to solve non-right triangles. So if it were a right triangle, I would just use SOHCAHTOA. I would just use my ratios. But this is for the non-right triangles. This is where we apply that. So then to get x by itself, I'm going to divide both sides by sine 34. And I've got 10 sine 52 over sine 34. And you want to be careful when you put this into your calculator because you want to make sure that you've got 10 sine 52 then divided by sine 34. Okay, so you can use the parentheses and things. 10 sine 52 divided by sine 34, which is about 14.09. So I'm going to call it x equals 14.1. I'm going to round it, so I'm going to squiggle up these equal signs. Okay, Justin, you've got x squared minus x cubed equals 12. Is that right? Am I reading that right? X squared. Okay. So Justin, let me finish this and talk about ambiguous case in just a minute, and then I'm going to talk, and then I'll get to your problem, okay? Okay. So the x is just finding this side length. This can be used for equilateral triangles, yes. But it kind of depends on what information you're given for the equilateral triangle. Okay, so somebody asked about the ambiguous case. So the ambiguous case is when you have two sides and an angle that's not included in that situation. Okay? So for example, if I have a triangle, I'm given a triangle, and I say that this is 50 degrees. Okay. This side is 9 and this side is 4. Okay. So I've got this angle, side, side. Angle, side, side. ASS. Angle, side, side. It is possible that you could, this side here, without having these two angles locked in, you could have this side swing in like this, and it could be, there could be a second triangle that looks something like this, where this is 9, this is 4, and this is 50. Okay, obviously not to scale, I know, right? But that is what the ambiguous case is that you might not know if it's that other one or not, right? And there's lots of really good animations about this. But so I could have these two like this, right? Or I could have it like this. Okay, so that's kind of like this one over here. All right, so that ambiguous case is where you don't know if it's going to actually be one or two triangles. Okay, so the way that you can look at it is, so I would use law of sines for this. So I know that sine 50 over 9, let's call this angle A, sure, equals sine of A over 4. So I'm going to cross multiply, and I get 4 sine 50 equals 9 sine A. I'm going to flip it all around. So then A equals sine negative 1 of 4 sine 50 over 9. And when I put that into my calculator, so I'm figuring out what this A value is out here. Okay. So we've got sine 4 sine 50 divided by 9. I get 19.9. So we'll call that 20 degrees. Is that right? Arc sine, 4 sine 50, 4 sine 50 divided by 9, second sine, yes. Okay. So that's 20 degrees. So that would mean that for this triangle to look like this, it would need to be 20 degrees. Okay. Now, when you are looking at this, so I always call this like the swing side. Okay, so this angle here is the one that's going to change. Okay, now what I would do is I would look at, okay, so we'll just call this like the ambiguous check. Okay, so so measure of angle A is 20 degrees, or it could be 160. Okay, now how do I know that? Oops, sorry, I'm way off the screen. Sorry about that. Okay, so if this version of the triangle is 20, then this version of the triangle would be 160 because they kind of make like a linear pair. Okay, so what I'm going to do is I'm going to add up and I'm going to see when I add each of the versions, like each of the options of the angle to the existing angle that I know happens, it's got to be less than 180, right? If it's over 180, I don't have enough angle degrees to have an angle up here. Okay, so I would do 50 plus 20, and I got to see, is that less than 180? Yes, that's true. 50 plus 160, is that less than 180? That is not true. So that means that there is only one possible triangle. Okay, so if these were both less than 180, then there would be two possible triangles, and there's lots of triangles out there like that. Okay, but that is what the ambiguous case is. It's where you've got this possible, like you can swing it in, and it could make two triangles. It could make an acute triangle and an obtuse triangle. Yeah, it's really cool. It's a really interesting and cool thing. And you could also even have these where there's actually no solution. There's actually no possible triangle that's like that. Okay. And that, when you set up the law of sines, when you set up this and you get an error, that means that that triangle doesn't actually exist. Okay. All right. So we're going to go to Justin's question because he's been waiting so patiently. Okay. So Justin's question is going to bring up one of my favorite things, which is polynomials. Okay. So he asked for us to solve x squared minus x cubed equals 12. I said cubed and I wrote squared. Okay. So let's look at this. So I am going to hope that this is factorable. So let's go ahead and I'm going to go ahead and I can take out, let's see, an x squared times 1 minus x equals 12. Okay, so I can factor that, but the fact that it equals 12 is not great because I want it to equal 0. Okay, and the reason why we want it to equal 0, the reason we want it to equal 0 is because then we can do the zero product property. I'm going to pull up Desmos really quick and put this in there. Whoops. Okay, So I'm gonna change my mind on what I'm doing here. Okay, so I'm gonna go ahead and I'm gonna rearrange this as it's negative x cubed plus x squared minus 12 equals 0. So I'm gonna go ahead and I'm gonna divide, or I'm sorry, I'm gonna just bring that 12 over, because now what we're looking at is we're still looking at that polynomial, right? Yeah, okay. So now I'm going to multiply everything by -1, so that's going to flip all of these signs. Plus 12. Okay, so now one thing that I'm going to do, and what I was checking on Desmos is when I'm looking at the graph of this, I'm going to go ahead and I'm going to put this in to the graph. And what you will see, and I know this is really hard to show you on here, but there is one rational root, because when you look at the graph, let me see. So the graph of this generally kind of sort of looks like that. Okay, give or take a little bit. Okay, so that's sort of what this graph looks like. So right here, there is a 0. There is a rational root. Now there are other roots because there are other things that we can figure out, but I'm going to start with that 0. Now I'm going to use on my NumWorks calculator. Oh, I love it so much. Okay, so I see that I've got 1 0, which is at -2, 0. So what that means is since I've got that rational root, then I know that one of my factors here is x plus 2. Again, I look at my graph, I see that there is a rational root at -2. So now I've got x plus 2 as one of my factors. So I need to divide this, and you divide this polynomial by x plus 2. Okay. So now I can get into synthetic division. Okay, so I can do synthetic division. So I've got -2 out here. And then I've got 1 and -1 and 0 and 12. Okay, so I bring the 1 down. -2 times 1 is -2. Add -3. That's 6. So here's 6. Here's -12. So a remainder of 0. Yay! No remainder. Okay. All right, so that means that I can factor this as x plus 2 times x squared minus 3x plus 6, which equals 0. All right, so x squared minus 3x plus 6, 3 and 2, 6 and 1. So that's not factorable, so we'll just go with quadratic equation, right? We'll just go with the quadratic formula. Okay, so x equals -b plus or minus the square root of b squared minus 4 times a times c all over 2a. So let's see. So that's going to be, oh my gosh, I keep going off the edge. Sorry, guys. So then that becomes 3 plus or minus root -15, right, over 2. So it's going to be 3 plus or minus I root 15 over 2. So my solutions are going to be -2 and 3 plus or minus I root 15 over 2. So you don't have to plug in and check, but you can do, well, it is kind of like plug in and check, but you just use the factors of 12. So you test the factors of 12 until you get one that that works for 0. Yeah, so if you do, like, if you look at, +1 -1, +2 -2, +3 -3, right? You can go through and you can check all of those, and you will find that that's the rational root theorem. So you will find that -2 is one of the roots. But for me, as a teacher, I kind of have a hard time giving non-calculator portions of exams. Sareem, I can't really read what your name is, but why not do long division? Oh, you could absolutely do long division. I love long division. But you could also do synthetic division, which is just a little bit more efficient. But you can absolutely do long division with these two polynomials. So Mr. Palterman or Patterman, I can't tell. What do you mean they usually say if 2 is a root, what are the other roots? Yeah, the 2 is the only rational root. And so what you can do is, there may be more, but all you need is 1. Because once you get that 1, then you can divide, and then you're it's almost like factoring, right? So once you get that 1 root, that's all you need. You can just divide, and then you get this, and then maybe you can factor this one too, right? So you could go through and do the whole rational root theorem to find all of the roots, but not if they're imaginary here, okay? And what you can also do is you can always just kind of graph it however you want, right? They give givens above the equation in some questions, so you can do synthetic division. Yeah, sometimes they will tell you, like, oh, one of the roots is this. But you can also see it on your calculator if you use Trace or you use Desmos or something along those lines. Okay. So Peyton, graphing trig functions are really tricky here because you need to have like the pi and the 2 pi and all of that. So it's really tricky for me to show those on this thing. Oh man, books, the best calculator on the market, that's NumWorks. So the NumWorks calculator will rationalize functions for you, or will rationalize denominators for you. It'll simplify radicals. It is so much easier to use and to navigate, finding zeros, finding maximums, finding minimums. It's less expensive than the other leading calculator on the market right now. Yeah, so if you want, you can send me a message and ask for a discount code. But I am a huge fan of the NumWorks calculator. I wish more people used it. I wish more students used it too, because it is really, really helpful. It's just a very intuitive, helpful way to. It just makes a lot more sense. And if you are interested in this, you can actually use, there is an app, or the app. So the NumWorks app, I know it's kind of hard to see, but it is exactly the same. So if you're not sure about it, go ahead and download the NumWorks app on your phone. It looks exactly the same. Yeah, but there's a bit of a learning curve because like Texas Instruments is kind of like, the one that has been sort of the leader for, for as long as I've been doing math, really. But there's just a lot more intuitive functions and functionality and things like in this calculator. it's really nice to use. It is approved for all the SAT, ACT, everything like that. But again, like if you're not sure, there's a free app that you can use it on, and I highly, highly, highly recommend it. Okay, let's see. Oof. Get a master's in mathematics. Oh man, good luck. But yeah, logs are pretty straightforward. Yeah, and yeah, so financial mathematics. So I really enjoy the NumWorks calculator. There are also things that you can use online, like the Desmos calculator and things like that. But Justin, I can't check your DM right now. But I'll take a look at it, and I'll message you back if I see any issues, because I'm gonna be done here in about 10 minutes. All right, guys, we got about 10 minutes left. So what should we do next? What's up next? Should we do more polynomials? Wait, what's happening? Ooh, Peyton, I don't think I have any. I don't think I have any graphing trig functions. But so just so Peyton, with the amplitude, period, phase, shift, all of that, I mean, it's really kind of straightforward once you have the format of the equation down. That you've got like the horizontal shift and the vertical shift and the amplitude and the period and all of that. You know, the period is basically like the distance between the complete wave, right? And then the amplitude is the height, like from the center line. So Luke, let me see, graphing logs. So again, guys, graphing on here, it's really hard to do other than like linear graphs. It's kind of hard to show those on this format. Is graphing is difficult. But let's do, you know what, actually, let's take a look at all right, let's look at this one. Okay, I'm going to give you guys a polynomial question. Okay, so we're just going to keep solving polynomials here. Okay, now these you can solve by factoring. Well, these are fun. Okay, let's do, so we've got 2x cubed minus 3x squared minus 32x plus 48 equals 0. Okay, and these you can solve by factoring. Five minutes to solve. I'll give you guys some time to solve this. It's fine. Yep, you can factor by grouping. Yep. Because there's 4 terms. Oh man, Justin, that is, yeah, that's a lot. Oh, so Justin, is that one of the solutions that you're given is I square root 2 minus x? So Justin, was there an equal sign in there? Or is it just for factoring, finding the zeros and stuff? Oh, finding the zeros. Okay. Okay. Yeah, we may not have time to get through that one tonight. But I'm gonna give that to my students and see what they can do with it. It's a semicolon. Okay, that's what I thought, because that was one of the things that's given, right? Okay. All right. So, as I said, you can solve this by factoring. So let's get into it. So when we're factoring, we've got these 4 terms. So when I have 4 terms, I can factor by grouping. So I'm going to factor this first set here. So 2x cubed minus 3x squared, I can take out an x squared from both of those. And I'm left with 2x minus 3. And then here I've got minus 32x plus 48. So I can take out a negative 16 from both of those. And I'm left with 2x minus 3 again equals 0. So now I've got 2 factors. One of them is x squared minus 16. And the other is 2x minus 3. Now I know I can't do anything more with the 2x minus 3. Okay, but x squared minus 16, I can factor that again because that is the difference of squares. Okay, so the difference of squares, that means that this is going to actually be x plus 4 and x minus 4 and 2x minus 3 equals 0. So those will be my 3 factors. Okay. So then my solutions are going to be -4, 3/2, and +4. Okay, so this is some fun factoring that we can do. Whoops. Hold on. I'm going to do this little puzzle piece thing. There we go. Hi, Maddie. I do not teach pre-calc. We usually tend to kind of stop around like trig. There's some pre-calc concepts that we can get into, but some things are some things are a little difficult to show on in this format, in this method. Okay. Yeah, Justin, I'll share with you how they go about that problem. It might take a little while because we aren't quite there yet, but I think in another week or 2. Okay. Oh man, books. So I usually stream. It's kind of been up in the air with when I stream, but I like to stream. It used to be always every Thursday. But we're tending to do it a little bit more frequently on Sundays and Mondays. So just keep an eye out. We usually try to announce kind of when we're going live a couple hours beforehand, so you know. How did I get 3/2? So it's because 2x minus 3 would equal 0. So you would add the 3 and then divide by 2, and you would get 3/2. Because if I plug in 3/2 to this x, that's going to give me 0. 2 times 3/2 would be 3. 3 minus 3 is 0. Ooh, Colin, what are you having trouble with in geometry class? Because that's going to kind of depend on what kind of tips I can give you. Ooh. Oh man, proofs. The way to get better at writing proofs is to write a lot of proofs and just keep writing them and writing them and writing them. What is kind of nice is that there are so many resources out there for writing proofs, and just making sure that you are doing all of the practice that your teacher gives you, all of the practice that's in your book or in your textbook or online when you can find it. But proofs are tough. Which is why I don't do a lot of them, especially in this kind of venue. It doesn't really work very well for doing proofs. But yeah, just keep practicing and practicing and practicing. And that's it. Have a plan before you go in. But you know that you're going to end up with, like, you're going to start with what's given. You're going to end with what you're proving, and everything in the middle is how you get there, right? So you've got to make sure that everything in the middle kind of makes sense. That's all the advice I can give you on that. All right, guys, have a wonderful week. Have a wonderful night. Hopefully this was helpful to a lot of you. It was fun for me, so hopefully it was fun for you to see a little bit of math. As usual, if you guys have any questions or concerns or anything like that, you can send me a message. Do one-on-one tutoring and online tutoring and all of these kind of things. So I will see you all next time. Bye. Yeah.